Okay, it's a great pleasure to introduce the second speaker this morning. Is Professor Charles Boyer from University of New Mexico at Albuquerque, and he will tell us about transverse Kähler holonomy and Sasakian rigidity. Please, Charles.
Well, first I'd like to thank the organizers for the very kind invitation. Unfortunately, and I'm very sorry, I'm not in Montreal, a city that I really love. But anyway, at least I'm virtually there right now. So, okay, so let's start. There we go. So my talk is based on joint work with Hongyan Huang and Christina Tennyson-Friedman. And I've often said that one should think of Sasaki geometry as odd dimensional Kähler geometry. However, strictly speaking, this is not true. It is much more accurate to think of Sasakian geometry as odd-dimensional algebraic geometry. If you think about it a little bit, you see that a quasi-regular Sasaki compact, all the manifolds that I'll be dealing with here would be basically compact. So on a compact quasi-regular Sasaki manifold, the transverse geometry is that of projective algebraic orbifold. So it's much more in tune with algebraic geometry. And so this was first pointed out by Nozawa in a paper that he wrote on deformation theory of Sasakian structures, that there are compact quasi-regular transverse Kähler flows that are not algebraic, hence they're not Sasakian. His examples that he pointed out were on compact nil manifolds of dimension at least 5. So this talk basically, and the paper that goes along with it, is basically interested in understanding or describing the difference between the category of Sasakian structures and the category of transverse Kähler flows. For this, we need to study deformation theory. So we recall the well-known Kodaira-Spencer deformation theory, but it's actually a transverse version that we need. This is due to Gerbal, Hefliger, and Sundararaman. And basically, if you have a transverse holomorphic foliation on a compact manifold, and theta of F is the sheaf of germs of transversely holomorphic vector fields, then one gets a Kurenishi space, essentially, this theorem says. There's a germ of an analytic space, the Kurenishi space, parameterizing the germ of the deformation. And there's a holomorphic map so that any two, well, you can read it here, right? So, parameterizing a deformation such that f of s prime is any germ of deformation parameterizing f by the germ s prime at 0. There's a holomorphic mapping from s prime 0 to s at 0. So the deformation, or these deformations, are isomorphic. So that tells you when you get equivalence. And the Kodaira-Spencer map is an isomorphism, the map from the tangent space at 0 to of the Kurenishi space to the sheaf cohomology H1 is an isomorphism. And then one gets, there's an open neighborhood of U in that space and a holomorphic map such that the germ is the germ of at 0 of the inverse image of that, right? And the 2 jet satisfies this equation, which basic obstruction to deformations. Now, in our theory, we need a technical condition for these holomorphic foliations, something that's called homologically orientable. That means that you have this, in these holomorphic foliations, you have the basic cohomology. And this basic cohomology, the 2n homology group does not vanish, where 2n is the codimension of the foliation. So the theorem that is very important to us that we use throughout is in our deformation theory is this theorem of Cassiemi, Aloe, and Jamira. And it says the following, that if F0 is a homologically oriented transversely holomorphic foliation on a compact manifold, M, with the compatible transverse Kähler metric, then there exists a neighborhood U of the germ of F0 in the Coronacci space, such that for all T, F sub T is homologically oriented and has a compact transverse Kähler metric, depending smoothly on T. So this basically is saying that holomorphic foliations of a Kähler structure remains Kähler as long as you have this homologically oriented technicality satisfied here, right? So this is very similar to, of course, this is the transverse version of Theorem of Kodaira and Spencer. So, and you know, the Cassiemi Aloe mentions in one of his papers, not in this one with Jamira, but he mentions that essentially you can think of the transverse version on a compact manifold behaving like the Kähler, transversely Kähler version, behaving like the Kähler structures on the compact manifold, as long as the manifold is compact. And this condition of homologically orientability is satisfied. So we're interested in the case that the holomorphic foliation is dimension 1. So we call that a transverse Kähler flow. So the first thing that I want to mention here in setting up this theory is a result of Molinio-Sergiescu that says that a homologically orientability is really equivalent to having a nowhere vanishing killing field that generates F. So you have a Riemannian foliation. So there's a little bit more going on here. I should have mentioned that. If I can, I don't know if I can deal with some of these. Acrobat has something, well, that I can write in here, Riemannian foliation. All right, so if I do that, does that do something? I don't know. Okay, so we want our foliations to be Riemannian foliations. Well, they are because they're transverse Kähler flow, but that's part of the hypothesis in the Molino-Sergiescu report, and I didn't mention it here. So these theorems that I mentioned before of Gervais, Hippliger, Sundararaman, and then the Cassiemi Aloe Jamira theorem, they will imply for us the following theorem: let Fj0 omega 0 be an isometric transverse Kähler flow on a compact oriented manifold M. Then so it's isometric, so it's equivalent to being homologically oriented. So then there exists a neighborhood U of the germ F0 in the Coronacci space such that for all T, the holomorphic flow F of T has a compatible transverse Kähler metric associated with it and an isometric transverse Kähler flow. So if you deform isometric transverse Kähler flow onto these, in this situation, you get, it remains an isometric transverse Kähler flow. So we can give a definition. A Sasaki manifold is a contact manifold with a compatible isometric transverse Kähler flow such that omega t is equal to d eta and c is the Reb vector field of eta. So this is yet another definite. There are many definitions, equivalent definitions of Sasakian manifolds. This is another one. I think so far the number is countable, so it's not too bad. A Sasakian manifold has an underlying contact CR structure, DJ, with a k-dimensional cone. That's what we call the Sasaki cone, a k-dimensional cone of Sasakian structures. Some people call this the Reb cone. I like to call it the Sasaki cone because the Reb cone of all Reb vector fields given the contact structure is infinite dimensional, much bigger. So these are only the ones that come from the Sasaki structure, that have Sasaki structures. Now, it follows from the work of Molino and his co-worker Sergiescu. As I mentioned, that there's a paper by them, and there are several papers by Carrier, that the analog of the Sasaki cone actually exists in this more general category of isometric transverse Kähler flows. And we call this cone the invariant cone. So this is an important ingredient for us so that we can deform in this invariant cone. Now, for transverse holonomy, we have the foliation version of Berger's Riemannian holonomy. This classification was done by Molino. I think it's in his book on Riemannian foliations. There are three types of irreducible transverse Kähler as holonomy groups, as one can imagine. They're UN, SUN, SP, n over 2, when n is even. Here, 2n is the real codimension. So these are the situation. Actually, it's the SUN and the SP that we're thinking about. So these correspond to irreducible Kähler, irreducible Calabi-Yau, and irreducible Hyperkaler, respectively. So we're particularly interested in the difference between transverse Calabi-Yau and the transverse Hyperkaler under deformations. How do they behave under the deformation theory, that since we're looking at transverse geometry to holomorphic foliations, that deformation theory that we talked about in the previous slides. So I mentioned that, well, some of the deformation theory, we started it a little bit in our book with Chris Galitsky, and also in a paper with Chris and Michael Nakamai. And then there was a more general paper by Nozawa on deformation theory. And there was a paper by Gorchis, Nozawa, and Tobin, a recent paper by Rosny, and then the paper that I'm talking about here by myself and Huang and Tennyson Friedman. So what we want to do is we want to know when deformations of Sasakian structures remain Sasakian and when they do not. Okay, so suppose we have a Sasaki manifold, S0. We'd say that S0 is stable if there, I could also use rigidity. I decided maybe rigidity was a little better, not to confuse with K stability, which is often talked about in the Sasakian context. So, but I call this, we call this S stability in our paper. If there exists, so it's S stable if there exists a neighborhood of in the Korenishi space, of the central fiber in the Korenishi space, such that Ft of JT is Sasakian for all T in N in the neighborhood. The first result is due to the first result that I mentioned. I'm going to mention in the middle. It's due to myself, Chris, and Michael Nakamai in the quasi-regular case, and then Nozawa in the general case, namely positive Sasakian structures are S-stable. So our first main result here is a generalization of this, which if you look back at the work of Kodaira and Spencer, it's just kind of following their how they do deformation theory, and then it's Cassiemi, Aloe, and Jamira that kind of transferred that to the transverse case. Okay, so so the first theorem that I want to discuss here is the following. If MS, let MS be a Sasaki manifold with vanishing first Betti number, and such that the basic Hodge number HB02, this is the basic Hodge number, vanishes. Equivalently, of course, that's the complex conjugate. Then S is S-stable. So it's this 0,2 component of the Hodge, basic Hodge numbers that is the obstruction to stability, the main obstruction to stability. So basically, this is what we want to, I would like to outline the proofs of two theorems, and this is the first theorem that I want. So are there any questions up until now?
So this hypothesis is automatically true in the Sasaki-Einstein case, positive in the Sasaki-Einstein case?
Yes.
Yeah. So
yes, they're all positive. That's correct. So this recovers. So there are several results that recovers the special case, the version due to Moriyama, who looked at Sasaki and transverse Calabi-Yau structures. They're S-stable when n is greater than 2. They're not when n is equal to 2. Of course, Calabi-Yau in that situation corresponds to Hyperkaler. So you look at the transverse geometry of that as K3 surface. And the thing to think about here is you think about K3 surfaces, and you take there are non-algebraic K3 surfaces. Right. So that's kind of what we're going to look at, the transverse version of that. Okay, so unstable structures, what I just mentioned, one can think of S1, non-trivial S1 bundle. If you have an S1 bundle over a K3 surface, that K3 surface, it's polarized, so it's going to be algebraic. But there are non-algebraic K3 surfaces. So this is the second theorem that I want to talk about. Suppose you have a 4n plus 1 dimensional Sasaki manifold with vanishing first Betti number. We're considering the vanishing first Betti number just because it's so that the Betti number doesn't get in our way. It might very well be true, or at least with some other hypothesis, more general hypothesis, but we'll, just for convenience, we consider the first Betti number being 0. And suppose it has a compatible irreducible transverse. Again, we're considering irreducible. That's necessary in this case, I believe. So compatible irreducible transverse Hyperkaler structure, then MS is S unstable. So again, think about the K3 surfaces that I mentioned. So let us just recall what a Hyperkaler manifold or orbifold is. It consists of a triple of complex structures together with a triple.
Is the point that this is analogous to the fact that you can deform something that has a Kähler metric of Hodge type and get something where it's still Kähler, but it no longer has Hodge metrics? Because in this case,
yes, that's correct.
So it's because you have Ricci flat things in the transverse directions, and so there's this theorem that you mentioned yesterday that it necessarily would have to be quasi-regular.
Yes.
So the definition would have to be quasi-regular. That's the gist of the.
Yeah, that's exactly what's going on. Yes.
Thanks.
Okay, so here's the Hyperkaler manifold or orbifold, and so we have this the complex structures satisfy this well-known algebra of the quaternions, right? So the idea then is its holonomy group is contained in SPN, so it is Ricci flat, as Jason just was mentioning. So it is Ricci flat with vanishing first Chern class, right? So basically, it's a null Sasakian structure, and as we talked about yesterday, null Sasakian structures have to be quasi-regular. There are no other Sasakian symmetries other than the Reb that generated by the Reb vector field. So a transverse Sasakian, so that's what that we were talking about. So yes, so this implies that transverse Sasakian are quasi, so the category of compact transverse Sasakian hyperkaler orbifolds is equivalent to the category of projective algebraic hyperkaler orbifolds. So Theorem Two shows that there are transverse hyperkaler manifolds that are not Sasakian. So the local deformation space is isomorphic to an open set in H1 in the cohomology of here of course it's the sheaf of transversely holomorphic vector fields, and the manifold is of dimension 4n+1 because it's transversely hyperkaler, and the foliation is one-dimensional. So if you think about stability, dimension 5 is quite special, right? So let's look a little bit about stability in dimension 5. So the first thing that we have, if you have a simply connected 5 manifold, when does it admit null Sasakian structure? Well, in a paper with Chris and Paolo Matsu, we showed that there exists, if you have a simply connected, first of all, if you have a simply connected 5 manifold, then that must be, if it has a null Sasakian structure, that must be one of the k-fold connected sum of S2 cross S3, of course, diffeomorphic to that, of course, where k goes from 2 to 21. And in that paper, we proved that they exist in the cases where, as long as k is not 2 nor 17. I mean, we did this, this was done by just looking at certain hypersurfaces in weighted projective space. And then my former student, Jaime Cuadros, he showed using complete intersections that one gets k equal to 17, but 2 still remained unknown until the recent paper of Cañas, Munoz, Schut, and Trale, where they give a different proof that k equal to 2 does have, so it doesn't involve complete intersections or weighted hypersurfaces. Okay, so it's now known that that a simply connected 5 manifold admits a null Sasakian structure if and only if it is the k-fold connected sum of S2 cross S3, where k goes from 2 to 21. Of course, 21 is the K3 surface, and all these other orbifolds, the other ones from K up to 20, they're all orbifolds, and they're orbifolds whose crepant resolution is, of course, a K3 surface. Okay, so the corollary to our theorem, any null Sasakian structure on a simply connected 5 manifold M is S unstable. So all of these things will be unstable. However, a regular Sasakian structure over Enrique's surface is S stable. So an Enrique surface is not simply connected, it has pi1 equal to Z mod 2. So what's going on here? But I mean, it's well known, of course, unlike K3 surfaces, Enrique surfaces are all algebraic. So that's clearly what's going on in the transverse direction, right? So the manifolds K from S2, the connected sum of S2 cross S3, K times, those manifolds admit both a stable and S unstable, S stable and S unstable Sasakian structures. And these are done, they're all have the first Chern class equal to 0, the orbifold first Chern class is equal to 0. So this is going to imply that up on, if you think about these things as Orbi bundles, S1 Orbi bundles over those orbifolds, that C1 of the contact bundle is 0. And so they belong to the same almost contact structure. So there's a natural question, is S stability at contact invariant? This is not a question which I'm going to answer here. This is, right now it's not known. And it seems to be probably fairly hard in the sense that what we do know doesn't quite work. So let's, that brings me to a paper that I wrote with Leonardo Maccarini and Otto von Kurt, which is contact topology. And there we're looking at positive Sasakian structures that are represented by Brieskorn manifolds. And in this case, you can use Brieskorn manifolds have Stein fillings. That is, if you look at that cone over the Sasakian manifold, because it's Brieskorn, you can fill that, you can do a resolution of that cone singularity such that you get a Stein manifold. That makes things a lot easier, right? So Stein manifolds, it turns out that, and these were studied especially by Jean Gut and by Otto von Kurt. So one can do floor homology on that Stein filling. The floor homology that one does is something called S1 equivariant symplectic homology. And one can come up with a contact invariant known as the mean Euler characteristic. However, in the null Sasakian case, it doesn't work because this Maslov index is 0. It's the positive mono. The Maslov index here is exactly the index, which what's called the Fano, we might call the Fano index when it's positive. That's what it's called, the Fano index. But here it's 0, and that everything breaks down in this floor homology of the Stein filling. We haven't. I don't know how to do that in the case of this index being 0. Okay, so let's present an outline of a proof of Theorem 1. Are there any questions any other questions before we get to that?
Just a comment. So the Stein filling, it's not a resolution of the cone singularity. It's a smoothing of the cone.
Yeah, it's a smoothing. Thank you. Yeah, absolutely. It's a smoothing. And that's why if you're out of the Stein so it's only Brieskorn. If you go to a general it's certainly known that general Sasakian structures has a holomorphic filling, but that holomorphic filling is not a smoothing. So this is a smoothing, and that's important. Thank you. Okay, so so the proof starts, if you look back at the paper, I think 1960 paper of Kodaira and Spencer and El Cassiemi, Aloe, and Jamira transferred this to the transverse case that we're considering. They consider this fourth order differential operator. And it turns out, of course, that the kernel of this, the solutions, AAT equal to 0, the kernel of this operator, describe elements of the Hodge cohomology group. So once you have that, then you can prove the following lemma. There exists a neighborhood N in the Kuranishi space S of the transverse Kähler flow, F0, J0, omega T0, in the Kuranishi space S, such that if you look at that should be a basic, well, okay, this is really basic Hodge. So I forgot the B in there. And I'm not good enough with this thing to be able to write it. I don't know how it works, but that should be a B in there. So HPQ of the foliation FTJT is equal to HP0 F0 J0, as long as P plus Q is equal to 2. This is, of course, if you go back to Spencer and Kodaira, that's what they do, and the proof just along those lines. I'm not sure how well this extends to when P and Q are don't add up to 2, but when they add up to 2, so for 0, 2, and for 1, 1, it holds. So furthermore, the holomorphic foliation has a compatible transverse Kähler form. Well, that just follows from the El Cassiemi, Aloe, and Jamira theorem that you can always deform and find a compatible transverse Kähler form. Why doesn't it work here?
Is a question.
A question?
Yeah, so are you just asserting a Hodge symmetry, or are you saying that there's also a vanishing? Is there something that's not written?
I'm not saying it's vanishing yet.
Okay, I see.
I mean, just saying that this equality holds. Okay, so as an aside, there's a paper of Gorchas, Nozawa, and Tobin. And as an aside, this theorem, they have a similar theorem, although it's not stated quite like this in their paper. And this really generalizes it to the transverse Kähler category. Again, we need it to be in the what they show is that they show that it's, I believe they show for all P and Q, that it's independent of the Reb vector field that you choose in the Sasaki cone. But we're not working in the Sasaki cone because we don't, a priori, we're deforming in this transverse Kähler geometry. So we're going to have a central fiber, which is Sasakian, of course, but we're deforming in the transverse Kähler. Okay, so this generalizes a result of theirs. Why doesn't this work here? I'm trying to get it. Well, maybe this with this. Yeah, okay. So this is better. I'm losing my technical abilities in my old age here. So, so the condition that H02 is 0 implies, of course, that the basic Euler class of this foliation. So think of this as the central fiber in this Kuranishi space, and so it's of type 1, 1. These are equivalent statements, right? Whoops. How did that? No. Okay, next. So the lemma that I have there implies that the basic Euler class is type 1, for all t in the neighborhood of f0, j0. So the basic Euler class, let's see if I can do this. So the basic Euler class is d eta for a Sasakian structure B. This is the, well, post. I posted it, but I don't know what that means. So it's, can people see this? The basic cohomology class of d eta sub B? Okay.
Yeah, we see it very well. Yeah.
Okay, so that's the basic Euler class. All right. So a theorem of Nozawa says that if the basic Euler class of ft jt, so for all t in the neighborhood of the central fiber, is type 1 for all t in the neighborhood of the Sasakian central fiber, so it is Sasakian, then there's a smooth family of Sasakian structures whose underlying transverse Kähler flow is ftjt. In fact, this is really the main theorem of Nozawa's paper that I mentioned. And that paper is called Deformations of Sasakian Metrics. So it's this is his main theorem. So if we use this lemma coming from, basically built on El Cassiemi, Aloe, Jamira, and Kodaira Spencer, together with what Nozawa did, then we can get our result, right? So since omega t, the transverse Kähler form is dt of eta t, this implies S stability. So this is basically an outline of the proof of theorem 1. So are there any questions at this stage?
It's just a matter of the basic Euler class is really the analog of the first Chern class. It's not the Euler class of the, it's just it's like a,
yeah, it's the Euler class. I mean, if you think of it as an orbifold, S1 over orbifold, right? I mean, so you can even use it in the irregular case. We somehow call this the basic Euler class.
But it's really,
so because it does coincide with the Chern class, of course, for an S1 bundle.
Right. So Euler class, you'd normally think of the Euler class of the tangent bundle rather than of the.
Oh, no, it's not the Euler class of the
Okay,
tangent.
it's the Euler class of the canonical line.
Yes.
Right.
Well, it doesn't have to be the canonical bundle, but it's a line bundle. It's the Euler class of a line bundle. I mean, oh, okay. So I'm okay. Any other questions about? Okay, so next we go on to the proof of theorem 2. So a null Sasakian structure S is quasi-regular, as we had mentioned before. So the quotient of the S1 action generated by the Rev vector field is a Kähler polarized hyperkaler orbifold, which represents the transverse hyperkaler structure with a Kähler structure, let's say, that we choose. There's, of course, it's well known, there's a 2 spheres worth of Kähler forms that one can choose. So we choose one of them, I1 and omega 1. That will be our kind of standard Kähler structure here. So the proof of theorem 2, which, if you recall, theorem 2 says that these transverse hyperkaler Sasakian structures, which are hyperkaler, transversely hyperkaler, that they are S unstable. So the proof uses the twistor space of a hyperkaler orbifold. So first of all, this twistor space is diffeomorphic to the orbifold X cross CP1. CP1 with its standard structure, not an orbifold structure. The orbifold structure is on X. So TX, of course, the twistor space is known to have a complex structure. So complex structure is, however, not the product. So this is best described by Penrose's double fibration, right? So if you have the twistor space, so there's a natural projection to CP1 and a natural projection to X. And so this gives a correspondence which says that points of CP1 correspond to complex structures IZ on X. So every point of CP1 gives you a different complex structure on X. And then points of X correspond to rational curves in the twistor space. They're called twistor lines, rational curves with the normal bundle 2n so of 1. So this was used by Roger Penrose in his description of the nonlinear graviton. So the complex structure on the twistor space is then given by looking at I of Z. So you can think of I of lifting I of Z to the twistor space. So just I of Z, and then P star. I should have another projection there, but I didn't. Cheated, I guess. So P star of I0, where I0 is the standard complex structure on CP1. Okay, so that's the complex structure of this twistor space. Whoops, that doesn't work anymore. I have to go up here. Okay, so yeah, question?
I think that the last formula you wrote there has to be corrected. That would be the product complex structure, right? So you're not just taking the complex structure on CP. So there's IZ. Oh, I see. And then you're
no. It's just you have a
on CP1. Yeah.
Yes.
Okay.
Yeah.
But
any other questions? Okay, let's go on to the proof. So, yeah, I mean there is a confusion about whether you think about things on the twistor space or on the underlying space. I mean the idea is that going back here that that this the twistor space encodes this different information, right? So anyway. So you have a complex structures, they give rise to the 2-0 form. And certainly this 2-0 form is a section. So you can think about it several ways, right? It's a section of the pulling back O2, the pullback of O2 to the twistor space, tensored with the two forms on the twistor space. Okay, and this represents but this one can think of for each fixed Z, you have a 2 form on X, right? And this, which represents the variation of Hodge structures on X. So that's the beauty of this twistor space, is encoding this information. Oh, that never works, right? So here. So for each Z in CP1, as I just said, the form omega Z is a section of H20 with respect to the complex structure IZ. Nope, keep wanting to use that. However, for only a countable number of points Z will omega Z lie in the integral Hodge lattice. Okay, so, right, because, well, that's pretty clear because Z here, you can have rational numbers, and those rational numbers, of course, are countable. So for at most a countable number of Z in CP1, we have that omega Z, the cohomology class, is H2 orb. So you have to, H2 orb is what over Z. So since you're working with orbifolds, the ordinary cohomology H2 will have its coefficients in Q in rational numbers, but not all rational numbers. It's only, so when you look at H2 orb, you're looking only at the special class of rational numbers that correspond to integral orbifold, right? So it's important to understand the difference between this, and I didn't go into it. I mean, it's described. It's described in chapter 4 of my book with Chris Galitsky in a lot of detail. I think it really goes back to Hefliger, who really sorted this out correctly. Yes?
You could work with Q here because you can always clear denominators. If you took
yeah, you can always clear denominators, but what I usually want is primitive orbifold classes, right?
Right. So it's the main point is though that if you just look at the span of omega,
I can't hear, sorry.
So you know, even if you used rational things and put in the weaker condition that omega is in the span of omega hits.
Yeah, that's correct. Yes.
So that might be a shorter proof.
Yes. Yeah. I mean, what you're saying is I don't really need this but I mean, I always think of it in terms of the orbifold cohomology. So anyway, since a hyperkaler orbifold is irreducible, we know that H20 or H02 is actually one-dimensional, right? So this is the H20 of the orbifold, which is the same as the basic H20 if you think about it up on the Sasakian manifold or the Transverse Kähler manifold. So it follows that all but a countable number of points, Z, we have the Picard group is 0, right? I mean, the point here is, of course, that if Z is not a rational number, then you don't have any line bundles, right? So Picard group is 0. So that gives us that is the complex orbifold XIZ is non-algebraic. Even as it's an orbifold, but it's not algebraic. So it doesn't have any line orbi bundles. I shouldn't say, so what I have here is pick orb. So these are orbi bundles, but it doesn't have any unless Z is a rational number up here. So lifting, of course, the whole idea here is because it's quasi-regular, these two categories, the category upstairs on the Transverse Kähler structure and the orbifold structure they're equivalent. Basically, they're equivalent categories. So the complex structures d eta, which it really means that this d eta cannot be a pure type 1-1. I mean, that's equivalent to this condition up here, right? So MS is S unstable. So that's an outline of the proof of Theorem 2. So any questions here? Okay, no questions? You know, I just saw a hand. Is that Claude? There's a question.
Not this time.
Yes?
No question here.
No question? Okay, well, that, oops, it doesn't. That concludes the talk, leaving 10 minutes for questions, which there are none, I guess. But anyway, I just mentioned where the relevant papers here are either in my book with Chris and papers therein, or this paper with Maccarini and Bancard about whether there are whether these S stability is a contact invariant or not. My guess is that it is a contact invariant, but I have no idea how to prove it, given that the techniques that we used in this paper don't work, at least offhand. One has to do something a good bit different. And then this is the paper which my talk is based on. So thank you very much for your attention.
So we still have time for some questions.
Can I ask a question?
Yes.
Hi, thank you for your talk. So going back to, I didn't want to ask the question then because it's a bit speculative, but can we talk about transverse Calabi-Yau situation, right?
Sure.
So
you want me to go back to the Calabi-Yau, or no?
I think, not necessarily. I don't think we have to. It's well, unless you feel we do. But I think you've established, if I understood you correctly, you've shown that because of stability, right? So you've established stability in that case if n is bigger than 2.
Yes.
So that would mean that any transverse scalar deformations will necessarily still be a transverse Calabi-Yau. That's what you've established, right?
Yes. 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 It's if you. Yeah. The idea here is that Calabi-Yau orbifolds are algebraic. They have Orbi line bundles, right? So as long as n is bigger than 2, and so that means that you can have a transverse Calabi-Yau. You can lift it up, and when you deform upstairs, you can think of, because it has to be quasi-regular. It's like deforming downstairs, and downstairs it's known, and that's one of the things that Moriyama had shown, that it's stable.
Right. So suppose I wanted, so what I would actually like to do is to deform a transverse Calabi-Yau, a compact manifold, in a way that breaks up the S1 action, right? So you start with a regular, the regular Sasakian situation, and then can you deform it maybe still as a contact manifold, or even in a way that is no longer transversely Kähler, but maybe it's transversely Hermitian, right? But so my question would be, what would be the drastic deformations? Do we have an idea of how to deform it away from the from a Sasakian structure in a significant manner?
Yeah. So you want to deform.
I want to ruin the S1 symmetry. Yeah, I want to ruin the vibration structure.
Yes. So I'm not sure what happens in the. I mean, there's. I think isn't it studied by Ryushu Goto? I don't know if he's in the audience, but I think he had studied, at least for Calabi-Yau, the deformations on the Calabi-Yau space. Just not the transverse geometry. So what happens there if you try to, I just don't know offhand.
Do we know how to even parameterize such sort of drastic deformations? The reason I'm asking this, I mean, being completely transparent, is if you're in the 7-dimensional real situation, which Jason Lotte explained earlier this week, you start with a regular Sasakian fibration over Calabi-Yau 3 orbifold, and then if we were able to deform it sort of in a systematic way away from the circle fibration structure, from the regular circle action structure, then one could try and look at the total holonomy and try and improve the total holonomy from transverse SU3 to actually G2. That's the, I mean, that's the evil plan behind the question, right? But I don't quite know how to parameterize the available deformations one could consider in order to try and solve the problem.
Yeah, so the idea, of course, in this transverse version is that you don't do that, right? You have that S1 bundle and you're just deforming the complex structure, the transverse complex structure. So I'm not sure.
I might want to do the exact opposite of what you're doing, right? That's the point. What are the wrong deformations to consider in your setup? I guess that's the question.
I mean, you can go back to the theorem of Gerbai, Hepfliger, and Sundararaman. They're deforming the foliation, certainly, as well as the complex structure. So they're deforming the holomorphic foliation. So I think if you, well, this, I go back here. Right, here's the theorem, right? So, there's a lot known about deforming these transversely holomorphic situations, right?
Sure. Okay, so I should probably go back to this.
Yes, yeah, that would be my suggestion, that you look there. Yes.
All right, thank you. Thank you very much.
Okay, thank you for the question. A very good question. Any other questions?
I have a follow-up question, sort of following on Enrique's question. So rather than looking at something where the holonomy is SUN or SPK, you could have something where, I mean, maybe it's not, maybe it's reducible. So you could have something that was modeled on a product of a, geometry looks like a product of a Calabi-Yau, or maybe a flat torus, you know, and a hyperkaler. So do your results generalize to that case? You still seem to conclude that the thing has to be quasi-regular in that.
My guess is that I could I just for simplicity, we just looked at the irreducible case to not get bogged down in what's going on. But that would be another step. My guess is that one should be able to do that, right? And show that if you have, I mean, of course, depending on exactly how you deform, but yeah, you could have a product of a Calabi-Yau and a hyperkaler, and certainly the Calabi,
have a quotient product, right? So it's good.
Yes, of quotients, yeah. Quotients. So I don't really know, but my guess would be that one can say a good bit more, that one could generalize the result.
The funny thing is, there doesn't seem to be a direct splitting theorem in this context, but since you know things are quasi-regular, you can apply splitting downstairs.
Yeah, you can. Yes, you can. That's what you'd have to do. Yeah, they can. Downstairs, you can look at products. Yeah.
Thanks.
Mm-hmm. I also have a question, which is much more than answered, actually. So, hi, Charles, it's Ilka.
Hi.
You mentioned at the beginning there is this alternative way of viewing a Sasakian manifold as equivalently being having that the transfer.
I'm sorry, I didn't hear exactly. What was that?
Okay, go back to your favorite new definition of Sasaki. Okay, where you say characterize it by the transverse Kähler flow. But on the
Uh-huh.
other side, understood, which is not the one I'm using usually. On the other side, you said if the transverse flow is hyperkaler, it's not possible to conclude what the upstairs structure is. Can be Sasaki or not? Did I get that well?
Yes. Yes, I mean, what's going on is that as soon as you have the hyperkaler, you're allowing in the deformation space, you're going to be allowing what we're showing is you're allowing non-algebraic geometry there, right? So
here comes my question. Are there other situations where the property of the flow is equivalent to the properties of the contact structure upstairs? Because this classification of contact structures is awful, right? It has way too many subcases.
Yeah, yes.
It would be whether one would get a point of view, a different point of view on putting some structure into the different classes of contact structures by looking at the transverse flow. But that means one would have to have a equivalence property. Do you see my philosophy?
Yes, I'm not sure exactly how to handle that kind of deformation in this context. I mean, so right now we're thinking of just keeping that that polarized structure and then deforming the complex structure within it, right? But as soon as you allow for larger deformations, then it's much harder.
Okay. So even alpha Sasaki or quasi Sasaki would be hard to incorporate into the picture.
Yeah, I mean, you don't have to worry about because of these null structures are quasi-regular. You don't have to worry about deforming in the Sasaki cone, but you would have to worry about deforming that transverse, the Kähler form in the class, right? I mean, isn't that what you're considering?
Oh, okay, I will have to think about it.
Okay. Yeah.
Some further questions, perhaps, or just let's thank Charles again for the result.
Thank you.